Before introducing new topics of this chapter, we will recapitulate today all the previous topics so that you are able to understand the remaining topics better. After light, sound is the most important among our senses. Sound is a form of energy, just like heat and light. Sound wave travels in the form of disturbance in the medium, and this disturbance is periodic in nature. The disturbance which is created by a source is periodic in nature. That means it repeats itself after a regular interval of time, and during this the particles of the medium do not move forward themselves, but the disturbance is carried forward. That was the definition of wave. Now, in order that sound travels or propagates, it needs three things. It needs a medium for its propagation because sound cannot travel in vacuum, and therefore we are unable to hear any explosion that happen in space. Also, on the surface of the moon, two astronauts cannot talk to each other because the density of air on the surface of the moon is very less than that of Earth, and hence sound cannot propagate. Another thing that sound needs is a vibrating body because any vibrating body will always produce sound. And finally, a receiver and a receptor. Sound is a mechanical wave. There are two types of waves generally. One is electromagnetic and the other one is mechanical. So, sound is a mechanical wave because it requires a medium for its propagation, and it is classified as longitudinal wave and transverse wave. I hope with the help of this diagram you are able to recall all the points related to longitudinal wave and transverse wave. The diagram here shows two springs. The mode of vibration in both the springs are different. The first one produces longitudinal wave in the spring, and you can see clearly in this the compressions, the region of compressions, these regions are the regions of compressions that are produced, and this one is a region of rarefaction. So a consecutive region of compression and rarefactions are produced. Why is that so? Because it is a longitudinal wave. So in this wave, the source moves from left to right. That means in this direction as depicted here. And the coil also moves from left to right, which means that in longitudinal wave, the particles vibrate along the direction of propagation of the wave. On the other hand, if you look at the transverse wave, this particular diagram, then you will observe regions of crest, this peak, and then regions of trough, the peak at the lower part. So this is the region of crest, and this is the trough. So there are consecutive regions of crest and trough. And as shown in the diagram, it is clearly seen that the particles are vibrating in a direction perpendicular to the direction of propagation of the wave. See, the energy transport is in this direction, but the direction of vibration of the particles is up and down, which is quite the opposite of that of the longitudinal wave. In the longitudinal wave, the regions of compressions are the regions where the density of the medium is high and therefore the pressure is also high, and hence the volume is less. On the other hand, the regions of compressions are the regions where the density as well as pressure of the medium is low, but the volume is more. No such variation is observed in case of a transverse wave. This particular table describes all the differences that can exist or that exist between a longitudinal and a transverse wave. Longitudinal waves are the waves in which particles of the medium oscillate along the direction of propagation of wave, while transverse waves are the waves in which the particles of the medium oscillate perpendicular to the direction of propagation of the waves. Longitudinal waves consist of compression and rarefaction, while transverse waves consist of crest and trough. Longitudinal waves can propagate through all the three different states of matter, while transverse waves propagate only through solids and on surface of water. You observe change in volume, density and pressure in the medium, but no such changes are observed in case of transverse wave. This particular table tells us the differences between compression and rarefaction on the basis of distance between the particles, volume of the medium, and density of the particles. I have already told in the previous slide about all the possible differences between compression and rarefaction. So what have we seen over there? That the particles of the medium are closer to each other than in their normal state, and that is why there is a decrease in the volume for a moment, and the density of the particles are higher than the normal. That means density of the medium particles are higher than the normal. On the other hand, in the rarefaction region, the particles of the medium are farther apart, and therefore there is a momentary increase in the volume that we have observed there, and density as well as pressure are lower than the normal. There are five important wave characteristics: wavelength, amplitude, time period, frequency, and wave velocity. This graph represents a longitudinal wave. From this graph, you can clearly see that wavelength is the distance between two compressions. B and F are two compressions of this wave. At the same time, the distance between D and H, which are the two rarefactions, the distance between them is also wavelength. But actually, the definition says that wavelength is the length of one complete wave, and hence the wave which begins at A and ends at E, the distance between A and E is also wavelength. So this is the definition of wavelength, and this is how you measure wavelength. Amplitude is the distance from P to B, and this distance BP is same as QD is equal to FR and is equal to SH for this particular wave. So these are the two definitions that can be obtained or can be understood from this particular graph. The time period to produce one complete wave or cycle is known as the time period of a wave. But frequency is just the reverse. The number of complete waves or cycle produced in 1 second is known as frequency. And therefore, the relationship between F, which is frequency, and the time period is given by this formula. Now, wave velocity is the distance traveled by a wave in 1 second, and therefore The formula for wave velocity can be given by wavelength upon time period. Since time period is 1 upon frequency, so another formula for wave velocity becomes frequency into wavelength. This particular picture shows you the comparison between two waves, wave A and wave B, and both of them are longitudinal in nature. Now, if you observe the spacing between the particles in both of them, you will clearly understand that why wave A has a longer wavelength, but wave B has a shorter wavelength. Wavelength and frequency are inversely proportional to each other for a constant wave velocity. Therefore, a a wave with a longer wavelength will have shorter frequency, and a wave with shorter wavelength will have higher frequency. This is a simulation of longitudinal and transverse wave. Initially, both amplitude and frequency slider are at minimum value. On adjusting these sliders, you will have to observe some of the wave properties such as wavelength, amplitude, and frequency for both longitudinal and transverse wave. I will now start with amplitude. On changing the amplitude value on this slider, you will observe the changes that are taking place in longitudinal wave and in transverse wave. The black pointer here will show you the variation of the amplitude in the longitudinal wave, while this green pointer will show you the variation in the amplitude for a transverse wave. So now on increasing the amplitude, please observe both the pointers as well as the changes that is taking place in the wave itself. Now this is the maximum value of amplitude. I have not made any changes in the frequency slider. It has been kept constant at some value. Now on decreasing the amplitude, again you will observe that the distance of the particles from its mean position is changing. When I'll run this simulation, it will appear to be something like that. Now again, I'm changing the slider on the amplitude slider. Please observe and note down the changes taking place in both the waves for better understanding. So this was for the amplitude. A similar sort of change I will bring in the frequency slider, and now again you will have to observe what happens in both of these waves. So this is the frequency slider, and please observe now what is happening here in the longitudinal as well as in the transverse wave. The simulation is now running, and please observe the variation taking place. Now, when this frequency was being changed, no change in the amplitude took place. The amplitude remained constant. And when I was changing the amplitude slider, the wavelength and the frequency remained constant. So if I increase the amplitude of the wave, suppose I'm now keeping this amplitude, I'm just fixing this amplitude at certain value, and now observe the change in the frequency. Observe the wavelength also. Please, the amplitude is not changing, but what is changing is the wavelength. Now on increasing the frequency, the wavelength decreases. While on decreasing the frequency, kindly observe the wavelength increases. So this is a major thing that needs to be observed. I hope you all remember that frequency and wavelength bear a certain relationship. They are inversely proportional to each other. So, but the wave velocity remains constant. So this is what happens in both longitudinal and transverse wave. But no change or variation is observed when you change the amplitude of the wave. I mean, no change in the wavelength is observed as well as on the frequency when the amplitude is increased or decreased. Please observe the two waves. This, this one has a larger wavelength or longer wavelength than the second one. So this is the wave motion direction in both of them. The lower wave is a wave with high frequency and hence the wavelength is smaller, while the upper one is a wave of less frequency and the wavelength is longer.